Welcome to Yugabyte DSS 2022. My name is Alan Caldera. I'm joined today by Val Kolenchenko, who is the product manager in charge of backup and restore operations, amongst other things. And today we're going to talk about best practices for distributed database backup and restore strategies. What is the purpose of backup? So the primary purpose of backups is to provide business and application continuity. So traditional relational databases like DB2, Postgres, Oracle, MySQL, SQL Server, etc., maintain a single copy of the data while online. And so backups are conducted in order to maintain business continuity in the event of a disaster. Say, the machine goes down or disk goes bad, something in that vein. Since Yugabyte DB maintains at least 3 copies of the database while online, the focus shifts more to application continuity and what we call extreme disaster situations. So this would be in cases of, if you had multiple regions and say 2 of your 3 regions went down, in that case, you would only have 1 copy of the data surviving, and then we couldn't really decide how to restart the system from that point. So we would have to restore from a backup in that case. So Yugabyte's backups are primarily for application corruption situations, or if the majority of copies of a tablet are actually lost. So what are some of the features of Backup Restore in Yugabyte DB? So the first is it can be run while the database is online. So there's no reason to take the system offline. It wouldn't be a very good, highly available database if you had to take it offline to back it up. So we can run while it is online. The second thing is it's a topologically independent backup format. That is to say that it doesn't matter how many nodes I have or what replication factor I'm using, whether it's 3, 5, 7, 9, or even replication factor 1, I can back up and restore to any topology or any number of nodes as long as I have enough space to actually restore the data to. Also, nodes are backed up and restored in parallel. So when we're actually doing operations, as I'll show, we actually will visit all of the different nodes and copy out tablets in parallel to the offline store. So you have a choice of file store targets. This would be some examples would be AWS S3 and its compatibles like MinIO, IBM Cloud Storage, Nutanix buckets, and I think there's probably a list of 20 or 30 other S3 compatibles out there on the market. Google GCS, Azure Blob Store, as well as NFS. This would include filers, data domain, Linux file systems, and also I'm aware of some companies out there that are actually providing their own compatible APIs so that you could basically back up using any one of those different formats. I think Scality comes to mind. So with regard to the 2 different APIs, for YCQL, our Cassandra compatible API, we can do backups and restores at the table or key space level. For YSQL, which is our Postgres compatible API, it is currently only done at the database level, and I'll explain why. So I'd like to introduce a core concept here called snapshots. And so let's think about how Yugabyte actually stores data in the system. So we actually store things in what we call SSD files or sorted string files. So basically, these are the key value store files that actually store all of your data. And so basically, when we have a snapshot, we basically take a hard link to the files that exist at that moment in time. So once a sorted string file is written, it is never mutated. Okay, so when I write a given SSD file, it just never changes. Okay, the only way it changes is that a subsequent operation is done, and then it's combined later in the compaction process to produce a new record, which produces a new file. So for each table and each tablet, there is a tablet ID.snapshots directory that actually contains all the different snapshots for that tablet. And so these actually contain the actual hard links. And we use hard links such that basically you can't remove, so that if we end up compacting or files underneath while the system is online, then basically we don't get rid of those old files until all of the links are actually dereferenced. What this has the effect of doing is that over time, if you have these snapshots build up, then basically we get kind of a storage increase, because now you're storing previous copies of the data as well as the current copy of the data. But when we typically at the end of our backup process, we actually will delete these snapshots and it will remove the hard link files. When Val goes into point-in-time recovery, we actually keep these snapshots on disk for a period of time that you specify. So backing up a database, what's involved in that? So the first thing is we need a place to put our backups. So we do this through our YB Anywhere product in the cloud provider configuration panel. So there you see the choices of various targets here: S3, NFS, Google Cloud Storage, as well as Azure Storage. And each one of these is a variation on a theme. Basically, you give it a configuration name, and then the proper credentials, whether it be an access key or secret, or your JSON for Google GCS, or your SAS token for Azure Storage. And then for S3, because there's such a wide variety of compatibles on the market, we also allow you to basically specify the name of the host where the S3 store is actually located, so that you can use your own S3 storage that's in your particular site. So once we do that, then we can actually go and create a backup. So we then go to the universe that we want to back up, and then we select basically what storage we're going to back up to, the namespace, or in this case, database that we're referencing. In this case, we're using Northwind. AWS has a separate option to actually decide whether a backup should be encrypted or not. GCS and Azure Blob Storage do this by default, but for compatibility reasons, AWS S3 maintains this as a separate option. We also specify the number of parallel threads, as I mentioned earlier. Parallel, we do all these operations in parallel, and so the thing to remember is we're always working at a tablet level. So we want to be able to run multiple tablets simultaneously, so that we're not stacking up one behind the other. So typically 8 is usually a good number, but what you will find is that you can increase this number as you want to reduce the amount of time that your backup takes. But that only really applies to the copying phase, and we'll get more into that. Finally, what we want to place in there is the number of days that we actually want to retain this backup for. So what's going on behind the scenes when we do a backup? So for example, here we'll take, since we started with a YSQL backup, The first thing we do is we check the catalog version. Then we actually create the actual snapshot. And then we'll actually dump the schema with YSQL dump and copy it to our S3 location. So in this case, this operation, because it's working with the catalog, is not done in parallel. So we do all this all at one time, and so this actually ends up taking quite a bit of time if you have a large number of tables and indexes. Once we finished dumping the schema, we check the catalog version again. I'll explain that more in a moment. And then finally, we export the snapshot that we took and we copy it to our S3 location. And then for each table, on the nodes that actually contain leader tablets, you remember we have 3 copies, so I don't need to make a backup of all 3 copies. I just need the ones that are the actual leader tablets. So I'm going to copy the snapshot directories to S3, and I'm actually also going to checksum these files so that I make sure that when I do a copy back during a restore operation, that I have a faithful representation of what got stored. Finally, if encryption at rest is enabled, then I will save the encryption key as well to S3. So why all the fuss with rechecking the catalog version? Well, the big reason is consistency. So the snapshot file that we backed up in the earlier step basically contains DocDB's notion of what the table scheme is, as well as the tablet information for each table. So it must match the number of objects, the attributes in every table, and the order of objects. So you can't just edit the file and say, okay, well, I forgot a table, I'm just gonna put one here at the end. They all have to match exactly in the correct order. If there is a mismatch, then the backup or the restore can actually fail at that point. You'll get a message to that effect. So once the backup is complete, we come back to the panel where we initiated the backup. And so we can drill into the information where it says, okay, here was the duration. Here's when the time will be expired. Since we selected 10 days, it moved it 10 days out. And then finally, I highlighted the location where the backup is actually stored. So in my case, I have this backup on backups.yugabyte.com in a specific folder. And this is a representation of how it looks when it's actually down in S3. So we have the snapshot info PB file with its checksum denoted by the SHA-256 designation on the end of the file, and then the individual tablets and their checksums. So let's go back now to restoring a database. So let's take this database backup that I did that was on an RF3 system, and now basically restore it to a single node cluster. Okay, again, and to demonstrate that this is topologically independent. So when I go to restore the data, I say, okay, I'm going to restore backup. I select the storage location, and then in the storage location, I basically pasted the storage location from the last panel that I showed you earlier back into this location, and said, okay, this is where it's actually stored, and then this is the target universe, and then finally the actual database name. The database name can be the same, or it can actually be different. Okay, as well as specifying any parallel threads. You also notice here that there is a selection here for table. That this modal actually is used for YSQL backups as well, which can go at the table level. In the future, we will perhaps have some facility to do YSQL table level backups and restores, but that is not at this point. Okay, so what's going on behind the scenes when restoring? So let's talk about the restore steps. So the first thing that restore will do is it copies the YSQL dump from S3 and executes the YSQL dump script to actually recreate all the tables and tablets necessary to receive the data. So this is where the topological independence comes in. We'll actually create new tablets that will have different designations on them. And so we will basically have to do that so that it can receive the data that we're going to copy back. I'm going to then copy the PB file down from S3 and import it. So basically what happens during this step is we basically map the tablets for each table. So we say, okay, this table foo had 24 tablets spread across 8 nodes. On this new system, I'm only on 1 node because I'm on RF1. So basically, I'm going to create 24 tablets on this 1 node to receive that. And then basically, it's going to map the tablet IDs that go across. Finally, I'm going to copy all the tablet snapshot data from S3 to all the tablet peers, which means I copy it while I only copied one direction, 1 copy. I have to copy down 1 copy for RF1, but if I'm RF3, I have to make 3 copies. Okay, so I'm going to copy it to all the tablet peers and verify the checksums. And finally, at the end here, I'm going to restore the snapshot and make it visible to the cluster. At that point, the restore is complete. Now I'd like to turn it over to my colleague, Val Kolinchenko, to talk about point-in-time recovery.
Hello, everyone. My name is Val. I'm a product manager at Yugabyte. And so I wanted to build on what we've discussed so far and talk about one more feature that we have in the product, which is point-in-time recovery. And then I will also talk about several features that are coming up in the next 2-3 months. So let's start with the point-in-time recovery. This is a feature which exists in many databases, including Yugabyte DB. And in its core, it's basically just the ability to restore a database to any arbitrary point in time, as opposed to restoring a snapshot, which you would restore to the time when that snapshot was created. With PITR, you can choose any time within the retention target that you specify and restore to that point in time. This is specifically useful for cases which we call recovery from user or software errors, which are the things like incorrect data modifications or accidental schema changes or things like that. For example, you accidentally drop a table. Applications stop working, they cannot query data anymore, and you want to recover from this situation as fast as possible. And you also want to recover so that you lose as less data as possible as well. And that's what PITR allows you to do. Since you can recover to an arbitrary point in time, and let's say you know that the table was dropped at 2 p.m., you can recover to like 1:59 p.m., for example, which will give you just 1 minute RPO. And you can actually go much closer than that. You can go up to 1 microsecond recovery with Yugabyte DB. Point-in-time recovery in Yugabyte is based on in-cluster snapshots. So as we discussed before, there are in-cluster snapshots, which are stored on the data volumes where the data is stored. And you can also copy snapshots into the cloud storage or into the NFS. So PITR works only with in-cluster snapshots, which means that once you move the snapshot into a cloud storage or NFS, you cannot use PITR with that snapshot anymore. But on the other hand, that makes sure that you can recover as fast as possible, which means that you also get minimal RPO when you use PITR. So again, PITR is a great feature if you want to recover from a user or software errors, and if you want to make sure that you get as less RPO and as less RTO as possible. Under the hood, as I mentioned, PITR works. PITR is based on distributed snapshots, or more specifically, it's based on a combination of periodic snapshots and MVCC, which is essentially a history of past changes within that single snapshot. So for example, if you specify that you want to have a retention target of 3 days, Yugabyte will create a snapshot every 24 hours and keep every snapshot for 3 days. And within every snapshot, it will also maintain 24 hours worth of data changes, which effectively creates kind of a continuous stream of history changes for the last 3 days, which is your retention target. And this way, you can restore to any point in time within those 3 days. And when you actually invoke a restore operation, Yugabyte will first locate the snapshot, which is the closest to the point in time you specify, and then use MVCC to kind of roll back within that snapshot to specifically that point in time that you want to restore to. Now let's talk a little bit about what is coming up next. In the next 2-3 months, we expect several new features. First of all, it's point-in-time recovery management. So I've just talked about what point-in-time recovery is and how it works. The biggest limitation that we have right now is that it only is available in the core database, and there is no kind of orchestration or management around it, neither in YB Anywhere or in YB Managed. And that's what we are currently working on. In the next release, you will have YB Anywhere API, as well as UI, which will allow you to manage point-in-time recovery in your cluster, enable or disable point-in-time recovery for a specific database, as well as restore to any point in time when you need it. Another feature that we're currently working on is what we call Backups 2.0, which is essentially a set of improvements in performance and cost around backup management. And the first part of it is essentially kind of the new architecture and new implementation behind the backup and restore mechanisms. In the current version, in backups version 1, what happens is that there is more centralized approach to those things. There is a script that runs on the YB Anywhere instance that manages all the backup and restore processes. In the second version, instead of that, we will deploy a sidecar process next to every single node in the cluster, and every instance of that sidecar process will manage backup and restore for that particular node, which means that the process is just more distributed overall and much more efficient. And it also means that it's more scalable. The more nodes you have, the more data you have, the more nodes you add into the cluster, the more instances of that backup management process you have as well. As a result, we see significant performance improvements both for backup and for restore processes. We see around 4 or 5 times improvement there. And it also means lower resource consumption, lower CPU consumption, lower memory consumption as well. The second part of Backups 2.0 project is essentially an optimization of the way how we copy the files into cloud storage or into the NFS. So the idea is that, let's say you create a regular full backup on Sunday, and you copy all the files for that backup into your S3 bucket or Google Cloud Storage bucket. What happens next is that on Monday, Tuesday, and every other day after that until next Sunday, we will actually copy only those files that has been changed since the last snapshot. So we still will create a full snapshot in cluster on every iteration, but during the step when we copy those files into the cloud storage, we will only pick those files that has been changed since the last backup. So on Monday, we'll pick up that delta for Monday. On Tuesday, we'll pick up the delta for Tuesday, and so on. And therefore, when you restore, let's say you want to restore to a state which you had on Tuesday, the system will locate the backup for the full backup which we took on Sunday. We'll also locate the delta for Monday, delta for Tuesday, and then use those 3 parts to restore your data. The result of this is, first of all, it means that backups also work faster. We need to transfer much less data on average to the cloud storage, and therefore it takes less time to create a backup. But probably even more importantly, this means significant reduction of storage and data transmission costs. Like again, we need to transfer less data, therefore we need to consume less traffic between the cluster and the cloud storage, and we also need to store less data, which minimizes the amount of storage that you need. All right, so to summarize what we've talked about throughout this talk, the core of Yugabyte DB backup restore functionality is the distributed snapshots feature, which essentially allows us to create a consistent cut of data across multiple nodes in the cluster. Snapshots can be created in cluster, or they can also be offloaded into a cloud storage or into NFS. And we also provide management capabilities on top of that in YB Anywhere and YB Manage to create scheduled backups and also provide those integrations with cloud storages and make sure you have the seamless experience with backup and restore. In addition to that, point-in-time recovery allows you to quickly restore from user or software errors with minimum RTO and minimum RPO. So if that's what you're looking for, PITR is the feature that you want to use. And finally, Backups 2.0 project, which is coming in the next 2-3 months, will provide multiple performance improvements and minimize the cost of data transmission and the storage for the backups that you create for your data. Thank you very much.